Good afternoon, everyone. Welcome to another TACO Commercials Focus Tuesday. This is a nice one today on pump curve selection and project builder. My name is Brett Zerba. I'm an applications engineer with TACO, and I recognize quite a few of the names as I scroll through the list here. Thanks for coming back, and I'm sure you're sick of listening to me talk and hearing my voice. But again, thanks for your time. Thanks for your time. If you could do some hand waving, a couple of you do some hand waving so I know you hear me and see me. Uh-oh. Uh-oh. Anybody? Can you hear me, Rich?
I can.
Okay, I see some hand waving now. Whew, thank you, William. Hallelujah. We get nervous sometimes after all the snafus we've had recently. Again, TACO Tuesday. No handouts today. Rich Medairos, who will introduce himself shortly, will be the main presenter. I'll be monitoring questions. Ask away. Ask away. These, some of the things are subtle, important topics here that for today's presentations are subtle that we want you to pick up. So if you're unsure of something, type it in and ask away, and we'll try to make sure we answer all the questions as we do every week. And roughly 24 hours after today's presentation, look for an email. Most of you have been through the ringer here. You know what we're talking about. It'll have the recording attached to it, or access to the recording, as well as your PDH certificate if you need that. So be ready. Be ready. And so that's what we're looking for. We got some hellos too. Hello from Wisconsin. I like that. I like that from Wisconsin. Kevin, Stephen, and Jamin. Thank you very much for that. Anyways, TACO, privately held company, third generation. Johnny White Jr. Cheryl Merchant's been leading the team through the pandemic as we're coming out of it more and more. That's all we can say about that. That's all we can say about that. And then as we come out of the pandemic, we got the supply chain issues, and our team that's getting our parts and products are doing a heck of a job. Hats off to them for what they do on a daily basis to keep us as close to our schedules as we can. And I'm sure all of you are living it in some parts of your lives, if not your business life, your personal life, or shopping life for Christmas, or store life for supplies at the grocery stores. Anyways, let's digress. So again, HVAC, pump curves and selections, and project builder. That's what we're going to cover. Mostly will be on curves and selections, and then there's a little tool that we'll show at the end. Hopefully, Rich will get some time to show that. That might make your life a little easier. Because personally, if this tool was around when I was on your side of the fence, I would use this project builder, and I would exercise my my TACO rep, as much as I could. I would send him all the information and let him do all the selections, him or her. They're a great team out there. Our reps, second to none. That's what Project Builder would allow me to do. So thank God on that. So Mr. Capusta, glad you made us. Joe Britt, thanks for popping in. We ought to let you guys teach this course, for God's sakes. I don't know why we're not letting folks like Joe and Rich, you are going crazy here. Rich's friend is running the beach again. She runs that beach a lot. So Rich has a knowledge of these pump curves. And you know, Rich and I were talking before today's presentation a little bit about another troubling job, situation for some bigger pumps out in the field. So if something comes up on the pump curves, and you have a project or a startup or something that rings your bell, ask away, because it may help us answer some questions and lead you down the right path here. So I think that's enough yapping for me. I'm going to turn it over to my good friend Rich Medairos and let him take it away. Take it away, Rich.
Thanks, Brett. This is Rich Medairos. I'm one of the senior systems engineers here at TACO. Just to give you a 5-second introduction to my background, I am a mechanical engineer. I specialize in the engineering and design of HVAC systems. I am a PE registered in several states in the United States, and I've been doing this for several years. And today's topic is all about pump curves, pump selection, and if we have some time, we'll touch a little bit on Project Builder. So let's get into the topics today. So we're going to go through the process of selecting a commercial pump. We're going to talk about how to read pump curve or pump curves. We're also going to touch base on Project Builder. And then as Brett, and we'll have some questions at the end. But as Brett said, please, if you have questions during the presentation, please type them in, and Brett will ask me to pause periodically so that I can answer your questions. And if there's a question we cannot answer, we'll make note of it and get back to you guys. So let's get into a very, very simple diagram. And this diagram shows us a very simple closed loop pressurized system. And we know it's closed loop pressurized because we have an expansion tank right here. And closed loop means it's not open to the atmosphere. And the expansion tank is helping us control the pressure in the system. So in this particular case, we have two pumps, and we're going to make a selection for one of these two pumps. And we're going to round up the numbers a little bit. So we're not going to use the exact numbers on this little diagram. So I'm going to put a little arrow over here. And we're going to actually select a pump that's a little bit larger than what's physically shown here, just for the fun of it. And we'll select the pump that's 1,200 gallons per minute. And we'll round the system resistance from 55.2 feet. We'll go to 60 feet in this case. So we got 1,200 gallons per minute at 60 feet. And that's going to be our initial pump selection. Like a little note of that. Brett, if you could make a note of that just in case I forget the numbers.
Yep.
Go from screen to screen. I might forget what number I'm on here. All right, so, but before we do that, let's talk a little bit about the most common pumps that are used in our industry today. So here are the two of the most common pumps. And now there are other variations of these pumps, but I wanted to focus in on at least these two because they are the most popular. And as the diagram, as the picture indicates, the pump on the left is called a frame-mounted end suction pump. And it gets its name frame-mounted because the pump is in fact mounted on a frame down here, built out of channel iron. There is a drain pan underneath the pump, if I could point that out to you, and you should be able to see a little hole in the drain pan right here where you can connect a pipe, and then you can lead that pipe to a floor drain in your mechanical room. By the way, from these TACO frame-mounted pumps, the drain pan is a standard configuration, so you don't have to specify it as an option. And then obviously the pump itself, which I'm pointing to right now, and then also the electric motor. And underneath this guard here, there is a coupling. And I'm not going to get into the details of the mechanics of the pump today, but I did want you to be oriented toward the basic configuration of the pump. And it gets its name end suction from the fact that the suction side is on the end of the pump here, and the discharge is along the top. And whenever you have an end suction pump, the angle between those inlet and the outlet is always 90 degrees. So there's a nice 90-degree angle right there. And one other characteristic of an end suction pump is that, generally speaking, the suction size is larger than the discharge. So for example, if the suction was 4-inch, the discharge might be 3-inch. The pump, the motor assembly are bolted to the frame, and that implies that the motor shaft and the pump shaft, if I can kind of make a little sketch over here on the right, and so this little, let's assume that this is the motor shaft here, and then the pump shaft is over here. They have to be aligned within 5/1000ths of an inch, both well, actually in all three directions, in an angular dimension, in a horizontal dimension, and in a vertical dimension. And then those two shafts, the motor shaft and the pump shaft, are connected by a flexible coupling. So those are some of the basic characteristics of an end suction pump. The next most popular pump that we see out there today is called the vertical inline, And it gets its name vertical because the pump shaft and the motor shaft are in the vertical orientation. So there's the vertical line right there. And it gets its name inline from the fact that the suction side of the pump, let's just kind of pretend we have a pipe over here. This is the suction side, and I can tell that it's the suction side because the fluid flows through the pump, through the bottom, up into the impeller, and then runs around the volute and then out of the discharge side. And one of the characteristics.
Looks like you've been practicing, Rich. You've done some awesome sketches this morning.
Yeah, I know. This is pretty good, isn't it? It's not bad.
Perpendicular and around the corner and everything. Holy
Yeah,
moly.
I know it. Just kind of make a little pipe shape there, a little pipe shape here. And so one of the characteristics of an inline, as the name implies, is that the pump suction flange, the size that it connects to the piping system on the suction and the discharge are exactly the same size. So if this happens to be an 8-inch pump, it would be 8-inch on the suction and 8-inch on the discharge. And then the other characteristics are that this happens to be a split coupled, which means if I'm, again, similar to what I did before, we have the motor shaft coming down vertically, and then the pump shaft comes up from the pump base vertically. And because the pump motor, let's use the words pump here, because the pump, the adapter is what this device in the middle here that connects the electric motor to the pump, that's all machine fit. And so therefore, because it is a machine fit, it does not require a flexible coupling. It actually has a split billet aluminum. You can just see it in this photograph here. You can see it in the background. So it does not require alignment because it's machine aligned. And because of that, it does not require alignment in the factory, nor does it require alignment in the field. As opposed to the base mounted pump, it's aligned in the factory to within 0.005 of an inch, and we recommend that it get realigned in the field after the pump is installed in accordance with our installation manual. And because today is all about selection, I'm not going to go into details in terms of installation. But I just wanted to highlight a couple of the most common pumps that are used in our industry today. There are other pump configurations, and if we have some time at the end of the discussion, if somebody really wants to take a look at some of those, I'll be happy to display them, and we could chat about those a little bit. So before we move on, Brett, do we have any questions from anybody out there?
Oh, we're in good shape.
Good hands. How's that?
Good hands. Allstate.
Allstate. Yeah, that's the Allstate insurance company. You're in good hands. Okay. All right. So now we're going to go live to TACO's website. So I'm going to click on Google here and then go right to TACO's website. And we're going to use, this is the home page for TACO's website. And we're going to use the pump selection tool to make the selection for the commercial pump represented by our simple diagram. So I'm going to click over here on, so we're live right now. So this is not a demo screen. I'm live on our TACO website. So I'm going to click on selection tools, and then on the left-hand side, I'm going to click on project builder initially because I'm going to come back to this later. So I want to make sure I'm logged in. So now I'm going to go over here to pump selection. So when I go to pump selection, I open up the TACO pump selection app, and this is where I get to fill in the information. So the first little box here is where we choose the pump type. And in this particular case, we're going to go with a standard pump. Each one of these little circles is a radio button. I could choose an OE pump, self-sensing pump, standard pump, or a high efficiency pump. But for today's selection, I'm going to focus our attention on a standard pump. So I'm going to click on that radio button for standard pump. And then in the next box is where I enter the information regarding flow and head. And I believe we said our selection was, I think I said 1,200 gallons per minute for today's selection.
12
and then
6.
Also 60 feet of head. Now, where it says minimum efficiency, if I wanted to, I could put in a value under minimum efficiency, but I recommend if you're using the software to leave minimum efficiency at 0, and that way you can see all of the selections that the software has to offer.
Hey, Rich,
Yes.
before you go too much further, Andy asked, what are OE pumps?
OE stands for optimized efficiency, and in our case, they happen to be a pump that can be fitted with an ECM motor drive assembly. The actual motor is a permanent magnet motor, and we offer those in a range from 3 horsepower up to 30 horsepower. So you can get a commercial pump anywhere from 3 to 30 horsepower in a permanent magnet motor married to a Danfoss variable frequency drive, which gives you an optimized, what we call an optimized energy pump. I can hear my dog in the background growling. I tell you what, Brett, why don't you entertain the troops for 1 second, and I'll grab my wife and make sure she takes care of the dog.
So we have another question from Joshua. Could you use the selection tools without logging in on the website? And the answer is yes. You do not need to log in on the website to use the selection tools. In order to get the best results from Project Builder, we recommend you log in. So that way the projects are saved, and you can go back to them anytime you come back in. But again, you do not have to log in to use any of our selection tools. We don't spy on you. Matter of fact, there's a video on our website from Johnny White, the owner and president of the company, that says, we will not use your email addresses with anybody else or send them around. That's his promise from the top. And, so we continue to do that. So
I'm back, Brett.
Yep. So I was answering Joshua's question about can you use the selection tools without logging in on the website, and I said the answer is yes, you can.
Yes.
But I suggested maybe if when we get into Project Builder, you'll show them why you might want to, though.
That's correct. Yeah, I think that's a great way of looking at it. So we've put in the flow in the head, and I've recommended that you keep the efficiency at 0. And for options, for now, I'm just going to leave these default options the way they are for right now. And I'm going to come back to that a little bit later. And now the next category is say choose the pump. And as we talked about initially, if you'll notice, we have the commercial pumps listed in the order of popularity. So on the left-hand side, we have end suction is the most popular, and then the vertical inlines are coming up in popularity. I would expect, and I think, Brett, you would agree that we think that the vertical inlines are going to bypass the end suction for popularity in the next couple of years.
Yep.
And then we also have other pumps, and as I said, if we have some time at the end of this discussion, I'll show you what some of these other commercial pumps look like, and they would be the horizontal split case, the vertical split case. And then on the right-hand side, if you notice, we have inline circulators. Those are the smaller pumps that are used in a combination of applications, but we're not going to focus in on those pumps today. We're going to just talk about the larger commercial pumps. So
Rich,
now that
I think this is a great time to answer Jim's question. Quick explanation on closed coupled pumps.
yes, a closed coupled pump. So a closed coupled pump, the pump is mounted directly to the motor, rather, is connected directly to the pump. So I'm going to bring up a picture of a close coupled pump. Let's see, we want end suction for a moment, and I'm going to zoom in on this photograph. This one is the photograph that I'm just pointing to here. That is the end suction base mounted pump. And the one on the left, I'll zoom in a little closer. This is called the close coupled. I think that was the question, right, Brett? And as you can see, there is no base associated with this. And the electric motor is bolted directly to the pump casing. And as it turns out, the impeller is connected directly to the motor shaft. So this pump does not require field alignment because it's already aligned because of the machine fit. So hopefully that answered Jim's question.
Yeah, the easy explanation, the motor shaft is the impeller shaft on a closed coupled pump.
Correct.
I mean, yep.
All right, so we'll go down here where it says choose pumps, and today I kind of like the KS, which is what we showed initially, a split coupled pump, a vertical inline split coupled pump. I'm going to click on that, and then click on the little orange button here that says search, and now the software is going to, oops, there it goes, yeah. So it's making several recommendations, and in a moment, I'm gonna go through this with you as to why I would pick one pump over the other. It's gonna go back and forth here in a moment. But I'm going to pick the one that's second from the top down. So I'm going to click on that. These are called the thumbnails. And then I'm going to click on that pump curve. Well, let me zoom in a little bit because the data that I'm displaying over here, grab my pen. I generally refer to this data up here as narrative data. This is what the software has actually calculated for the specific. In other words, we asked specifically for 1,200 gallon per minute at 60 feet of head. This particular selection is running at 1160 RPM, and the software has predicted that the impeller diameter should be 12.35 inches. We'll see what that means in a minute. Hold on 1 second. It's one of the challenges of working remote. And so it also displays the size of the size of the pump was an 8x8. Let me erase that so I don't. Yeah, it's an 8x8, and again, as I said earlier, this is a vertical inline, which means that the suction size is the same as the discharge size. This particular pump happens to be 84% efficient at the design operating point, and we'll get into this in some detail, at the design operating point of 1,200 gallons per minute, 60 feet of head. The horsepower that the pump is consuming at the design operating point is 21.58, and the non-overloading horsepower is 27.02, which I will talk about in a few minutes. And also the net positive suction head for this pump is 10 feet. Now I want to erase those red lines, and because the pump has a non-overloading horsepower, which means that's the maximum horsepower that this pump will demand at 1160 RPM and 12.35 inches. That means that when I go over here to motor, I want to select the next largest motor, and in this case, I want it to be 30 horsepower. So if you'll notice, at the design operating point, I have 21.58 horsepower, so I could select a 25 horsepower motor, but in order to comply with the with many engineers' specifications where they want the electric motor to be non-overloading over the entire pump curve, I would make a selection at 30 horsepower. So that's what we're going to do for today. But now I'm going to zoom in on this pump curve, and then we'll get a better picture, get a little bit clearer picture of what the pump curve looks like. Brett, any questions popped up before I start getting into some of the details of the actual pump curve and how to read it?
Oh.
All right. So whenever I look at a pump curve, I always divide the pump curve. Oh, I'm sorry. I should tell you what thing is what here. So the red line represents the pump curve that would provide us with 1,200 gallons per minute. That's this point down here. There's 1,000, 11, 12, 13, 14, 15. So that I put that tick mark at the 1,200 gallons per minute. And over here on the left, that's 60 feet. So there's our design operating point where those 2 points intersect. So now we have to have a pump curve, and I believe we said that the impeller diameter would be 12.35. Is that what we said a minute ago, Brett? 12.35. Well, I'll go back to that value in a second here. I think it's 12.35 inches. And I'm just going to do a quick back and forth here just to make sure I'm not. Yes, 12.35 inches. So there we go. Okay, so this red line shows us the pump performance if we cut the impeller from its original full size of 13.5 inches down to 12.35 inches. And the red line represents the performance of a 12.35 inch diameter impeller spinning at 1160 RPM. Grab my pen one more time. Spinning at 1160 RPM. So the software has done a couple of things. It has made a recommendation not only in terms of the pump configuration, but has told us what it recommends for an impeller diameter in order to run at the design operating point of 1,200 gallons per minute, 60 feet. So that's what the red line means. The blue line is our system curve. And if you recall, when I showed you that simple chilled water diagram at the beginning of our discussion, I said it was a closed loop pressurized system, and the closed loop pressurized system always starts at 0 flow and 0 head for a closed loop pressurized system. So we have the blue line is the system curve, the red line is the pump curve, and where those two intersect is the design operating point. And again, ours is 1,200 at 60 feet. If I trace, let's grab my bouncing ball here. If I kind of put my finger on this pump curve and I trace all the way along the entire pump curve, you'll notice that at the design operating point, well, I should go back and just define this a little bit. These diagonal lines are lines of constant motor horsepower. So this first diagonal line down here that I'm highlighting is 10 horsepower motor. The next one is 15, 20, 25, 30, and 40 horsepower. So at the design operating point, you can see that the horsepower is just above the 20 horsepower dotted line and it's below the 25 horsepower dotted line. But if I follow the pump curve over the entire pump curve, I see that it crosses the 25 horsepower, and that's why I'd have to install a 30 horsepower motor in order to comply with the specification requirement that many engineering firms have that say that they want the electric motor to be non-overloading over the entire pump curve. And that's where NOL, that's our terminology, which is the maximum horsepower that this pump will consume. And in our case, I believe it was around, let's go back here, around 27, yeah, 27.02 horsepower. Let me get rid of that for a moment here. Okay. So we've talked about the pump curve at 12.35 inch diameter, spinning at 1160. And by the way, with this particular red line representing the pump curve at that impeller diameter and that speed for this specific pump, no matter what we have for a system curve, if I have a different system than what's displayed here, this is the design system curve, but what if I have a different system curve? The only place that that pump can operate is wherever that new system curve intersects the pump curve. So no matter how many different system curves I might draw that represent the actual system configuration, it will always operate on the pump curve. It can never operate off of the pump curve. Any questions, Brett?
Yeah, there's a pretty good question here. Your selection is an 1160 RPM motor. Obviously, there's commonly three choices, right? 1760, 30, 3500, 1160. Any recommendations of which one to use when? Higher head, lower flow, higher flow?
Yeah,
NPSH?
actually, I was going to get into that in a minute.
Okay. All right.
So the most popular speed that people would select pumps at would be 1760 RPM. And the reason for that is because the electric motor is a little bit less expensive and typically has a shorter lead time than 1160. But I wanted this select this one for a specific reason. I wanted to show people the characteristics of the curve itself. So whenever I look at a pump curve, I always break the curve into three parts. I kind of put a bubble around here. Actually, let me change colors because it gets a little confusing with the, let me go with a green here. So I divide the pump curve into three parts, and I kind of put an imaginary bubble around it. So I have a bubble on the left side here. I have another bubble in the center third. There's another bubble there, and then another bubble down here. And so I always try to select the pump so that it's in the center third here. So you can always divide the pump curve into three parts and use your imagination, or you could draw it like I did. And then try to select the pump within this center section. So going back, and that's why I need to go back and forth a few times here. Going back to the initial selection, if you recall, I'm going to click up here where it says pump, back to pump results. That'll show me the multiple selections I had to choose from. So even though the thumbnails are relatively small, I can't read the values. I'm just looking at the shape of the curve. And so what I tend to do immediately is eliminate the pumps that perhaps would not be all that desirable. This one, it's too far to the left, too far to the right, too far to the right. This one, a little bit too far to the left for my interest. This one's pretty good, actually, just on the tail end of the center third. This one is also in the center, but chances are I wouldn't select this pump because I'm fairly close to the minimum impeller diameter, and the efficiencies tend to drop off a little bit. So let's keep going on here. Yep, whoops. Let me get rid of those green lines and scroll up a little bit. So if you'll notice, so like I said a moment ago, this is a reasonable selection. This one is a reasonable. This one is a little bit far to the right, but it's still okay. But the one I picked right here is the one that I like the shape of most of all. And again, I use that little example of dividing the curve. I don't have to have the big giant curve in front of me. All I need is the thumbnail, and I want to be in that center section, which is why I selected that pump. So getting back to our pump curve here, you can see that if you divide the curve into 3 parts, you kind of want it to be in the center. And it's nice that the curve is not at the extreme. It's not the extreme where it's the largest impeller diameter. It's not the smallest impeller diameter. It's kind of in the middle. And that gives you lots of room to move left and right, up and down, in order to accommodate perhaps a slightly different system configuration than what was originally anticipated. Okay. The other thing I like to point out on the pump curve is, let's grab another color here. Let's do, how about pink today, Brett?
There you go.
I like pink.
Hey, we got the 5th generation of the white family is 2 girls, so pink is a
So
great.
in honor of the 5th generation of the white family, we're going to stick with pink today. Okay, so these lines here, these are curved lines here. These are lines called lines of constant efficiency. And if you'll notice, as you ride down the system curve, you perhaps, let's assume for a moment that you had this design operating point. I'm going to kind of round this off. I'm not going to be super exact. But let's say that the design operating point happens to be 1,000 gallons per minute on this system curve and approximately 40 feet of head. Now, obviously, my curve is not exactly that value, but it's close. And if you'll notice, it crosses this efficiency line right here. And so as I ride down the system curve and change the impeller diameter, then my efficiency drops off. So one of the characteristics of trimming an impeller is that you reduce the impeller, ultimately you reduce the wet end efficiency or the pump efficiency. So a lot of people are actually starting to think about maximizing the impeller diameter and using pump speed to get to their design operating point. And if you do that, the efficiency lines remain relatively constant and they're almost parallel to the system curve. So in other words, if we put in a 13.5-inch diameter impeller, it would generate this flow in head where it intersects the system curve, but that's not where we want it to run. So we would reduce the speed by using a variable frequency drive to emulate the 12.35-inch diameter impeller. And the advantage to that is that I get to save the efficiency. In other words, the efficiency would remain relatively constant. It's almost at 86%. So if I slid down the system curve by manipulating the pump speed as opposed to trimming the impeller diameter, I would actually get more efficiency out of the pump. So a lot of engineers are considering going in that direction. And then the last value that I want to show you today on the pump curve is that our design operating point is 1,200 gallons per minute. If I follow that line vertically upward, where it intersects this curve at the top, this intersection point right here, and these are values of 5, 10, 15, 20. So the net positive suction head required by the pump is going to be 10 feet. And I think we saw that in the narrative information on the previous screen. I'll go back to that in a minute. And the units for required net positive suction head are always in absolute value. So all pump manufacturers provide this data for their pumps, but keep in mind that the value is 10 feet in our case, 10 feet, and the units are 10 feet, I'll abbreviate it FT, 10 feet of water column, this is generally WC, water column, and then a lowercase a for absolute. So the full name for the net positive suction head pressure required by the pump is 10 feet water column absolute, because these are absolute pressures, whether you're using feet or meters or kilopascals. It's in absolute pressure. Okay, so that covers all of the pieces and parts to a pump, or how to read a curve. Now I'm going to kind of give you some tips on how you can use the information once the pump is physically installed if you're trying to do some troubleshooting.
Okay,
Any questions before I go on?
Yeah, we have a couple questions. You kind of addressed one of them, but before we get into, well, it says, I'll read it verbatim. In the real world, would you go with a 12.5 impeller rather cut off 0.15? It looks like you may improve the efficiency with a slightly higher GPM. And you touched upon that many folks are looking at maybe increasing the impeller diameter a little bit, or somewhat, to increase the probably get a little higher efficiency. Maybe as long as you stay below that 30 horse or whatever. I'm not sure what your specific statement might be in regards to that.
Yeah, so that's absolutely correct. I mean, you can, when you're making a pump selection, you may want to select a slightly different impeller diameter, but there are some restrictions that you have to keep in mind. So again, the reason you would pick a perhaps larger impeller diameter is that you know that the pump, or you're specifying the pump, whichever way you're looking at it, will have a variable frequency drive, and to operate at your design operating point, you know you're going to have to change the pump speed. So if we selected it at the 12.5 inch, which I think is what that question was, you would be at this black line right here, which is a slightly higher flow and head at 1160 RPM. And in this case, if you'll notice, if we follow that black line all the way down, it also does not cross the 30 horsepower line, so the 30 horsepower motor would work. But to hit the design operating point for balancing purposes, assuming that they were accurate relative to the pressure drop in the system, you would have to slow the pump down. And again, in this particular case, it's 1160 RPM, and perhaps you only need to reduce the speed a small amount. The actual speed is, by the way, proportional to the impeller diameter. So at 12.5 inches, we said that the actual impeller, in order to meet this point at the same speed here, would be 12.35. Well, if I took the ratio of 12.35 divided by 12.5, and I'm going to do that on my calculator while I'm chatting here, 12.35 divided by 12.5, that's the ratio of the impeller diameters. If I multiply that, which comes out to 0.988 times 1160, then it would actually run at about 1146 RPM. So I'd have to slow it down to 1146 RPM in order to hit the design operating point. So hopefully that answered that question, Brett.
Yep, and then here's a nice question right here from Jake. Are there any concerns over speeding a pump with a VFD?
Yes, absolutely. So when it comes to overspeeding a pump, so in most cases, you can manipulate the variable frequency drive to run the pump at a higher speed, but just because you can doesn't necessarily mean you should. So you should always check with the factory if you want to overspeed a pump, because the mechanical parts of the pump are rated at certain speeds. So the faster you rotate a pump, which includes the shaft and the impeller assembly, including the bearings, by the way, they are limited to how fast they can spin and still maintain their structural integrity. So whenever someone wants to overspeed a pump, perhaps let's say they have variable frequency drive, and in this particular case, they have a let's say they had the 12.5, well, no, the 12.35 inch diameter impeller, and they wanted to speed it up a bit to drive it up the system curve a little bit, and they still wanted to stay under 30 horsepower, perhaps they could drive it up to this range here. Maybe, for example, I'm just making up a number without doing a calculation. Maybe they could spin it at 1200 RPM, and maybe that relates to, well, it will relate to a slightly higher frequency than 60 hertz. But before you go ahead and do that, you should check with the factory and see that if mechanically it can withstand the higher speeds, so that structurally it will stay together. Okay.
Excellent.
All
There's
right,
another
so
question. There's another question. I hate to even ask you this, but I'm gonna. Why do
go
we
ahead.
need to check NPSH in closed loop system?
That's a great question. So
It is.
you
It's
should always,
interesting.
in any type of pump configuration system, whether it's open loop or closed loop, you should always do a calculation which we refer to as calculating the available net positive suction head, because the available pressure always needs to be greater than what's required by the pump in order to ensure that the pump will not cavitate. And that we have another discussion, another presentation that goes into detail. I don't have the time to do it today, but basically what we're saying is that the absolute pressure at the suction side of the pump has to be a certain value or greater than that value in order to ensure that the pump doesn't cavitate. And in a closed loop pressurized system, since the cavitation is a function of the pressure and the temperature, which ultimately translates into what we refer to as the vapor pressure, if you have a pump, for example, that's at the top of a building, say in a penthouse, and it's a very hot system, perhaps it's running around 200 degrees Fahrenheit, and you have a relatively low pressure, you could potentially have less available pressure than what's required by the pump. So my recommendation is to always do the available net positive suction head calculation and compare that against the pump to ensure that your available pressure is always greater than what's required to ensure that the pump won't cavitate. Good stuff. I love
Yep.
these questions. Okay. So we've talked about a whole bunch of things here. Now let's talk a little bit about some of the information on the pump curve that you can use that's useful for you for troubleshooting. So one of the first things that we always ask, somebody calls up and they'll say, well, I've got this pump, it's 1,200 gallons per minute at 60 feet, and it's pumping less than what we had originally anticipated. My question, well, how do you know it's less? They said, well, we have a calibrated flow meter on the piping system, and it's actually pumping 1,000 gallons per minute at, I'm sorry, it says pumping 1,000 gallons per minute instead of the predicted 1,200 gallons per minute. So you can use the pump curve and go in the pump curve, and you can see at 1,000 gallons per minute, I'll follow that line vertically up. And remember what I said earlier is that it always has to operate on the pump curve. So if it's pumping 1,000 gallons per minute, that indicates that the pressure, instead of being 60 feet, the resistance in the system is no longer 60 feet, but it's 65 feet. So if we take very accurate readings across the pump, and again, we're using a KS pump in this particular case, which means that the inlet size and the outlet size are the same, which means we do not have to correct for velocity difference. So that the pressure differential, if we're using calibrated pressure gauges, it should indicate that we have less pressure. That there's more pressure in the system resistance than what was originally anticipated, and that would account for the lesser flow. The opposite also holds true. We do get calls once in a while, and somebody will call up and say, hey, I installed the pump and we're running at 1,500 gallons per minute. And I'll say, okay, let me look at the pump curve. Where the pump curve intersects that 1,500 gallons per minute, the pressure differential is down here, which is 50 feet. So through accurate measurements, I should be able to determine that the pressure differential across the pump is 50 feet, and therefore we have less system resistance, which means that in reality, the system curve is going like this. It's not the best curve in the world. It's not too bad. But again, it can only operate on the pump curve, which means that the system resistance is less than what was originally anticipated. And if you were looking for 1,200 gallons per minute, you would have to slow the pump down in order to accommodate that slower speed. I'm sorry, lesser pressure differential. Boy, there was a mouthful, right, Brett?
I guess that got confusing.
Yeah. And that's a couple of troubleshooting tips. Another one is over here. So one of the other pieces of data that we sometimes ask for if somebody says they have a pump issue is that this value over here is called the shutoff head. In other words, if I begin to throttle back on the discharge valve only, that's extremely important. Let me just make a little sketch over here. If this represents my pump in the piping system, and fluid is running from left to right, there's the suction side of the pump, there's the discharge side of the pump. I have a valve over here on the discharge side. If I begin to throttle back on the discharge side of the pump, it will follow the pump curve all the way up to the left. If I shut off that valve, I'll get a pressure reading at zero flow. And in this case, at 65, just over 70 feet, it's roughly 71 feet. Now, that accuracy is usually within plus or minus 8 feet or so. So if I know that my if I know my pressure differential is approximately 71 feet at zero flow, and we only recommend that you close this valve for a few seconds to take that reading, that's called a shutoff head. You should be able to compare your field measurements against the published data, and it should be within 8 feet of that plus or minus, and that will help you understand whether or not you're operating on the pump curve. So that was some quick tips on what to look for. The other piece of information is the power consumption. If my pump was originally sized for 1,200 gallons per minute at 60 feet of head, we said was consuming somewhere around, I think it was around 22 horsepower. Let me go back to that other curve for a moment. Oops, whoops, what happened, Brett? Oh yeah, here we are here. That's this guy. We said that was around 21.5 horsepower. Something doesn't look right, Brett. What did I do wrong? Oh, I know what I did wrong. Let me do this again. Let me erase these lines. I got so excited.
That's the wrong curve.
It's the wrong curve.
That's what you did wrong.
That's what
Thanks,
I did.
Jim.
Okay. I got so excited there. I picked the wrong curve. Okay, let's go back here. So it was around 21.5. There it is, 21.5 horsepower. So we can measure the amount of power that's input. And typically what we would do if it had a variable frequency drive, we'd measure the power input to the drive, which is the volts and the amperage. We take into consideration the inefficiency of the drive, the inefficiency of the electric motor to arrive at the actual power being consumed. So if we can measure those pieces of information, we can generally determine if the pump is operating as originally designed. So I'm going to actually jump into Project Builder. Looks like we have some time to do that. Brett, are there any other questions out there before?
Yeah, there's a question that's been hanging, and you kind of touched upon it. This may be a good time, Mike said, to mention how power is cubed. So if you run at 66 hertz, you are at 33% higher power, which could overload the motor. Good point. Not
That's
really a
correct.
question, it's
Yeah.
kind of a statement.
So that's it. Yeah, that's a great observation. Sure, if you increase so someone asked originally, can I increase the pump speed? And the answer is yes. But what I forgot to mention is not only you have to check the mechanics of the pump, but you also have to check to make sure that your increased speed can be accommodated by the electric motor, which is a cubic relationship of the speed. So in other words, if I took, for example, if I wanted to increase the speed from 1160 to 1200, I take 1200 divided by 1160, and then I would take the cubic relationship of that, which comes out to about 1.10, which means that my new horsepower would be 10% greater, even though my speed increase was only, instead of 10%, was only 3%. My power consumption would be cubic relationship to that. So that's a great observation. Thanks for that.
Yep.
Good stuff. People are paying attention today, Brett.
Yep, smart people. Smart people. As usual, the audience is smarter than us, as usual.
They are. That's what I like. Okay, so now we've made a pump selection. I'm going to actually show you how to take advantage of the Project Builder software. So if you'll notice it, I can scroll down and this little sign here says Project Builder and it says Add to Project. I'm going to actually create a new project. So I'm going to scroll all the way down to the bottom. I'm going to click on this radio button that says Add to New Project. Click on that. Let me zoom in a little so everyone can see what's going on here. So I zoom all the way down, click on Add New Project. I'll have to move this down one more time here where I can type in the project name. We'll just call this Training. Oops. Did I spell that right? Yeah. Training, and I'll just put in November. Today's the 16th. Wow. We have like a week and a half till Thanksgiving. Did everyone get their turkeys this year? Hopefully they got them in time.
I don't want to tell people we got our turkey and we set up our Christmas tree and all the presents are wrapped and underneath it already.
Wow, I'm coming to your house for Thanksgiving. Have you got my present already?
It's already, baby.
Already.
Another bag of coal.
Okay, so we're going to add a product tag. So let's assume that the drawings that I'm working with call for this pump to be P1. So I'll put the tag number in there. Then I can go down here where it says attach documents. I'm going to click on that. And for today, I'm going to attach the submittal data and also the catalog. And scroll down some more. I'm going to press this button that says Update Project Builder. Press on that. And then go to Project Builder. And so what's really cool about this is that it's building a schedule for our pump. And if I should mess up, let's assume I mess up, for example, and somehow I shut off the computer or I lose power or I go out to lunch and I forget to do my thing. Once I've made my pump selection in Project Builder, I can now go back to my Project Builder. I'll pick up exactly where I left off. So there's training November 16th. And if you notice, I'm back exactly where I started. Now, obviously, if you have only one pump that you're selecting, it's not that big of a deal. You don't really need to use Project Builder, although I always recommend it. But if you get involved with projects like Brett and I do that have 20, 30, 40, 50, 100 pumps, you start putting that much time and effort into your selection process, it makes it extremely convenient to use Project Builder to save all of that information. So once I have created my selection in Project Builder, I can export this project. I'm going to click on that. And then over here, for now, I'm just going to download the zip file. And in the lower left-hand corner, it's going to show me the progress of downloading the zip file. And hopefully it'll run fairly quickly today. There it goes. So I'm going to click on the desktop here. I'm going to put in a new folder. I'm going to put a training, and I'll just call it 1116. So I can keep that in mind. Save that. And now I've saved my project. And now I can open up that zip file. You can see the documents that I saved. So there's that catalog. I saved the catalog. So all the information about the KS pump is now attached to my project. And then also the submittal data sheet. This is really cool. So I just put in the job training November 16th, but look at this great submittal data sheet. All of this information is already done for you. It's got all of the information about the pump. If I scroll down, you'll see the generic pump curve. And if I scroll down to the bottom, let me zoom in a little bit. I have the specific pump curve as part of my submittal documents. And I have all of the information that I showed before. So I have the narrative data on the left side here, and I have the pump curve, and I have the pictures. I'll scroll up. There's the generic pump curve. And then also all the information about options and dimensional data all in one location. And again, because it's in Project Builder, I can access this information from anywhere on the planet as long as I have a, what do we call that thing, Brett? Google and yeah, we'll think of the name of it. Somebody could type it in for me. A browser, that's the word I'm looking for. As long as you have a browser, you can access your information from anywhere on the planet. And so now that we're into Project Builder, which is really cool, we're going to close all the tabs here. we can also, let's go over here. Yeah, let's look at that. Oh, I saved it. So I'm going to go over here just for the fun of it. I've got training 16. Here's the documents. And also it creates a spreadsheet. So I'm going to click on pumps tab in the bottom here. So this is all the data. There's that pump, there's the tag number, all the information that we just asked for. And so you can cut and paste this and put it right on your drawings, right into your Revit files or your CAD files, whichever you want to do. So that's really cool. Now, the other nice feature is that once I can go back here to my selection. Once I've started Project Builder, now I can just add to it. So, and I'm going to do a very fast example. Let's say I want an expansion tank. I'm going to click on the T over here. My project's got an expansion tank. Let's say the system volume is 2,000. I'm not going to go through an instructional period. I just want to kind of do a quick demo here of the expansion tank selection, fill in all of this data, search, and I like this one here, so I'm going to click on that, add to project, and I'm going to zoom all the way down here because I want to put a tag on it. I'm going to put expansion tank -1, ET-1, attach documents, a submittal catalog. I've likened catalogs today, update Project Builder, and then go to Project Builder. I know I did this very quickly, but I wanted to just demonstrate that not only do we have the original pump tab in our schedule sheet, but now we also have an expansion tank. So I can add whatever I want in Project Builder very, very quickly, and everything is consolidated into one location. So Brett, we have a few seconds to answer some questions.
Yeah, we have a good question here. Could you please explain the pros and cons when we should use a suction diffuser?
Yeah, so a suction diffuser, let's go over here and look at, let's see. Can we, yeah, I think we can display a suction diffuser, can't we, Brett?
Yep, underneath
So we want products and we want pump
accessories.
accessories and we want a suction diffuser. There we go. So a suction diffuser can be used when we have a situation where we want to make a transition between a pipe, perhaps that's dropping from a header. So I'm going to make a little sketch here while I'm talking. So here we have an overhead header like this, and then we come off that header. Generally speaking, I like to make sure that people, well, let me do this. Let's put our header over here. Then let's say we have a horizontal pipe close to the ceiling inside of a building. So this represents the structure up here. We have a header. What I generally recommend is you don't come off the bottom of the header and you come off the side of the header. And then you want to connect to the pump. And so you put in an end suction diffuser. And this is kind of a gross little diagram, but you'll get the idea here in a minute. There's our end suction diffuser. Connect up like that. And that connection has a flange connection right there. And that's, so here's that pipe coming down into this, in the inlet, and then this is the pump connection right here. And that flange connects to our pump flange. And then I'm just going to make a gross little diagram here. It's not the best diagram in the world, but you get the general idea if I'm connecting to a vertical inline pump. And then on the discharge side, I have another flange and then the piping system. So the advantage of using an end suction diffuser is that it will allow you to change direction, make a 90-degree turn. Here's our 90-degree turn. There's our 90 degrees right there. And in a relatively close configuration to the pump. And the end suction diffuser, you can see from this photograph here, it's got little straightening vanes in there. And so that's what allows you to make that connection. So if you're trying to save space in a mechanical room and you can't get the long radius elbow and the, say, 5 to 10 pipe diameters, you can use an end suction diffuser to accommodate that. Hopefully that answered that question, Brett.
Yep.
Well, it's 1 o'clock. We're at the end of our time limit here. We could take maybe one more question.
Actually, Andy Souza has in parentheses Avengers Headquarters with question marks. Any idea what I like that. I'm not sure what he's talking about, but I figured I'd bring that up.
Oh, maybe he saw that on my Project Builder list.
Oh, maybe he did. Is that one of your projects?
Yeah,
Yes, he
that's one
had
of
a
my
project.
projects, Avengers Headquarters. If you click on that, um, actually, we can go into that project. Let's see. Let's just do a quick thing here. My projects. And then when that screen comes up, we can scroll down to Avengers Headquarters, and let's see what the Avengers Headquarters was specifying here. Am I going to be able to find it without running out of time, Brett? Look at all the projects I'm involved with. This is unbelievable.
It's not in alphabetical order, huh?
Not in
It's time.
alphabetical order today. Well, so it's the good news and the bad news. We did have a project called
Oh,
Avengers
you got to
Headquarters.
go scooting up.
So the folks at the Avengers Headquarters building, they consult with us all the time. They're always asking us different questions. Sometimes I help them with their superhero questions, but most of the time I help them with their pump questions. So, as I always like to say, let's go. And any last question before we sign off, Brett?
No, we're in good shape.
Well, thanks everyone for participating in today's presentation for TACO Tuesday with the commercial focus. And as we said in the past, today's discussion was all about pump curve selection and project builder. Hopefully you got something out of it. Thanks again, signing off and turning it over to Brett. Thanks, Brett.
Rich, great job as usual. Class attendees, thank you for your questions and participation, and thank you for your time. We'll see you in a couple weeks. Bye, all.